Thank you, first of all, to EPRV RCN to invite me to talk about my favorite star. Second of all, for those of you who are not keeping up with me hopping universities every 4 years, I am currently at the University of Birmingham, where I moved about a little over 3 months ago and started a faculty position. So in principle, I won't be hopping another university in 4 years' time. So this does come with another email for those of you who want to send me emails. Thanks, Johanna. So anyway, today I'm going to talk about how we observe the sun to basically learn about the stars in an EPRV context. So this group really doesn't need to know why it is we're doing it and why stellar variability is an issue, but just very quickly, this is the total amount of planets discovered cumulatively over the years, and as you can see, this is actually exponential growth because the y-axis is in log space. So we've surpassed about 5,000 exoplanets a couple of months ago, which is very impressive. But getting masses for these planets is actually really hard, and that is mostly because we sort of hit an RV barrier. If you look at semi-amplitude versus the year of discovery of the planet, with 51 peg over here in the beginning, then we were steadily pushing instrumentation and steadily pushing the models and the statistics that we did and to lower and lower semi-amplitudes. But since about 2008, 2009, we seem to be stuck at 1 meter per second. You do see that a couple of these points do dip below that line, but given that the color is significance of the semi-amplitude, you all know what that means, of course. That is partly, of course, because some of the instruments do not reach precision that good, but several of our instruments should be able to dip below that line and aren't. And it's really because you can only know your exoplanet if you know its host star. But in a way, it's also that you can only find your exoplanet if you know your host star. And this is because of the stellar variability, as you all very well know. This is a beautiful picture of the sun going through its magnetic cycle, previous magnetic cycle, going from solar minimum to solar maximum back to solar minimum. Now, if our sun is doing that, all the stars are doing that too. And radial velocity is a motion, so all these motions on the surface will inevitably screw up our measurements. If you want to know anything about how scary stellar variability is and all the different types of stellar variability, all the different timescales, all the different processes, I highly recommend that you go to that Google Drive and you watch Annelies' talk on stellar variability for a full overview. Whilst totally scary, it's an excellent overview of all the things that actually happen on the surface of a star and that we should, in principle, be taking into account. Now, what are the benefits from sun as a star observations? Now, in a way, the sun is the only star we know and will remain the only star we know that has no orbiting planets because we can remove them from the data. And that is very interesting. It's going to be really hard to ever say that about another star. This one, we are sure. And I know I'm sort of ignoring the whole planet 9 thing in this statement. But in a way, if we remove the motion of the solar system, we are left with a data set that in effect has no planets in it, making it the perfect star to learn about stellar variability. Now, I know what you're all thinking already, so I'll just start with the caveat for sun as a star observations. For how many stars will it be helpful that we study the sun as a star? Obviously, the easy answer is it's definitely going to be helpful for solar type stars because the stellar variability processes are very much the same. Now, it remains to be seen how easy we will be able to extrapolate to other types of stars that suffer from other different types of stellar activity on their surface. But for solar type stars, it will definitely be a plus. You can think of it this way: if we improve what we know about the sun and its effect on radial velocities, and in that way improve the way we can do simulations of stars, those simulations could potentially be easier extrapolated to other stellar types. Now, this is a big slide. I normally avoid slides with a lot of text, but given that this is being saved, I figured it could be a good reference point. So Sun as a star observations for EPRV is in a different ways that you can approach this. You can do simulations with technically aren't observations, I know that, but they can also be really good to match with observations that you do. So there are several out there that do full simulated spectra. There's a couple references there that you can see. Starry process also comes with open source code on GitHub. You can also do just simulating cross-correlation functions or average spectral line profiles such as SOAP and SOAP 2.0, which are all open source as well. Then you can observe the sun indirectly. So you can, for example, observe the sun through the moon or through asteroids. In case you would want to do that with your 3.6 meter telescope, you can obviously you can't point that at the sun, but you can point it to an asteroid like Vesta, for example. The light will reflect. You'll have some horrendous motions to take into account of the light path that was taken, but you can technically observe it indirectly that way. You can also go to resolved observations, so MDI, SDO, DKIST, whatever, and reconstruct an unresolved radial velocity from that. In order to do that from SDO, there's also an open source code, if you would want to, by Tamar Erwin. It's called Solaster, that deals with SDO data and how to get the measurements that are useful for us out of that. Now, but I'm mainly going to focus on the fact that we can do direct observations. Literally, you make another telescope, a solar telescope, specifically being able to point at the sun, and you stick it in your high stabilized spectrograph that you normally observe stars with. I want to point out that these direct observations of the sun also happen for non-stabilized spectrographs, have been happening for years for non-stabilized spectrographs. But obviously, from an EPRV perspective, we are interested in the stabilized spectrographs. Now, quickly about these simulated spectra. I know you all know this, and I know Nadesh has said it. This is also Nadesh's paper that I'm pointing out. So in the top row, you see the photometric effect of spots on radial velocity, and in the bottom row, the photometric effect on radial velocity from plages, which are the bright regions. And as you can see from the Y scale on the left, we're staying well between like 2-3 meters per second. Well, 3 is a stretch, 2 meters per second. The middle panel and the right panel is moments of low activity, where you can see for spots, sometimes it's like literally a straight line at 0, and high activity moments where you do see some sort of variation, but you stay well within those 2 meters per second. Now, if we look at convection, suppression of convective blue shift in the top row, then that scale goes from 0 to 10 meters per second throughout a magnetic cycle. Again, with the zoom in during solar minimum and solar maximum. And then in the bottom, you have the total effect, which is suspiciously close to the suppression of convective blue shift because it's so dominant. So this was all simulations, and this was simulated with models. This is what we think the solar radial velocities would do, and then confirmed in the same year by reconstructing from MDI. And you see the same pattern here. This is not the same picture. The previous one, and they go back, that was simulations. This one is observations, but it is the exact same thing. Now, reconstruction from SDO data, what Tamar and Rafi and Tim Milburn, etc., all have been doing, basically takes the different measurements that SDO does, like the continuum and the intensity of your sun, the Doppler velocity of your sun, the magnetic flux values of your sun, and then applying some corrections, combining all the pixels, and you get a radial velocity out of that. Now it was shown recently by doing this. So this is the entire magnetic cycle of the sun, and in the top you see the radial velocities that changed during that magnetic cycle with that same pattern that we saw from Nadezh's paper, but now it's stretched, of course. And then in the bottom, you see the hemispherically averaged unsigned magnetic flux. And as you can see, it has the exact same pattern, and they correlate extremely well. So as far as a tracer for radial velocity variations for solar type stars and solar-like activity goes, the unsigned magnetic flux seems to be a really good tracer. Now, let's go to this direct data. That's presumably why you came. So I'm mostly gonna focus on the solar telescope that is feeding into HARPS-N for the simple reason that that's the one I use. So the solar telescope feeding into HARPS-N was also the first one that got plugged into a high stabilized, high resolution spectrograph. So on the right, you see the telescope that we look at to stars. That's the TNG, it's a 3.6 meter telescope. And on the left, you see our solar telescope, which is much better appreciated in this picture, where you can see how tiny it is, because these people are not giants. These people are regular people like me, you and me. So you can see the side of the dome that houses the big telescope next to them on the ladder. It has its own little platform, has its own little dome. It happily sits there and observes the sun for us. So we started observing in July 2015, which means we have a staggering 7 years of observations by now, but which also means that we haven't yet observed during solar maximum. We take daily 5-minute exposures, trying to average over the solar oscillations. And we start observing at 9 a.m. till the TO or the observer decides that, hey, we want to do calibrations, stop. Which obviously this timing differs throughout the year and with different telescope operators. Now, I'm happy to report that after several years of observing the sun, we can confirm that Jupiter is a planet in the solar system. We very clearly detect Jupiter and all the other planets for that matter. They're all in there. But Jupiter being our most massive planet, obviously it's the most obvious one in the data. For those of you who frown, it's like, how do you detect Jupiter after 1 year, whilst obviously we are at a 1-year orbit and Jupiter is at a 12-year orbit? That is because we're in the solar system and you really detect the synodic period, not the orbital period of the solar system planets. Anyway, we can correct for that. As I said before, we use JPL for it, which at any given point can tell you what the radial velocity motion of the solar system itself is, and you can move from the barocentric frame into the heliocentric frame and effectively get your data set without any planets in. Now, when we were observing for a while, we noticed that we had a daily downwards trend. So this is some of our data, radial velocities versus fraction of a day, where 0 is midnight and 1 is midnight again. The blue line is just there for your eyes to guide you. It's horizontal at 0, and the red line is a fit to that data, which clearly goes down. And you can actually sort of see it by eye as well, that that data clearly goes down. It's not a lot, but given that we're hunting for teeny tiny signals, it is large enough. Now, why is that? Well, we're claiming to observe the sun as a star, but in a way, it's not really, because the sun is obviously not a point source in the sky. It is resolved in the sky. It rotates just like any other star, and it rotates on an angle from our point of view. Now, what that means is that the redshifted and the blue shifted part of your of the solar surface will differently be atmospherically extinct whilst it moves through the atmosphere. Now, that is a problem, and that is what creates that downward trend, because the different hemispheres of the rotating surface are simply differently atmospherically extinct, because one is higher in the atmosphere than the other. Now, luckily, we know that angle of the sun. We know the location of the sun at any given time, and you can do some clever angles and formulas. And if you want to know the nitty-gritty, it's all explained in our 2019 paper, so that you can actually correct for this effect. The unknown in this equation is the extinction coefficient of your atmosphere. But that's where you can be really clever and actually use your own data to get the extinction coefficient of the day that you were taking observations. Because we're taking multiple observations per day, whilst it's moving through the sky, basically what it means is that if you were to plot, say, signal to noise versus the hour angle of the sun, you see a downward slope. And that is simply because the sun is higher or lower in the atmosphere, that we actually receive more or less flux. The slope of that line is directly related to the extinction coefficient, which you then can extract and use, and also in a way use to throw out all the data that might be impacted by clouds, for example. The cool thing is about this that we know for the last 7 years, know the extinction coefficient through time for La Palma. It looks like this. So overall, La Palma has an extinction coefficient around 0.10. Well, in the value as we use it, again, the nitty-gritty is all in the 2019 paper. Some days we have an absolutely amazing atmosphere. As you can see that the low point here goes to 0.05. Other days, being rather close to the Sahara, we jump up to about 0.4 when we suffer from Sahara dust in Kalima, and the atmosphere gets a little reddish. Anyway, let's go back to the solar data. So just so that we don't lose view of what we're doing here, this is now our data set. Radial velocity in meters per second versus time. It's 6 years of data, not 7, but it's 6 years of data. There's no planets, it's corrected for an atmosphere. This is genuinely just stellar variability, photon noise, instrumental noise, systematics, but it's not planets, definitely not planets, and you can treat it as a star. If we were to want to detect, let's say, an Earth-like planet in an Earth-like orbit around a solar-type star, such as us, and this is what you're looking for. Several of you have probably hear me say this loads and loads of times, but what we're all trying to do is to find the blue wiggle in the black mess, and that is sort of why we're all still having a job in a way. But that is also just a very nice in-your-face picture as to why finding small planets, and especially small planets at long periods, is so terribly, terribly hard to do. Okie dokie. So we were doing so well that Xavier just decided, why stop at one solar telescope when we can have two? And so they built also a solar telescope that feeds into HARPS, which is in the southern hemisphere in Chile. And you can see it over there. It also has its own little platform and little dome, and it also happily observes the sun for us since October 2018. I thought I had adapted the fact that it is not 5-minute exposures, but clearly I have not. So they take very short exposures, so they do resolve the solar oscillations. By the way, the solar data of HARPS, given that HARPS is an ESO instrument, several of that data after a proprietary period is publicly available through the ESO archive. Now, the power of having both HARPS-N and Helios came very, very quickly. La Palma's day and the Chilean day do overlap. And as you can see here, the blue is the HARPS-N solar telescope data on a random day, and the orange is the HARPS solar telescope data on a random day. And this jump that you saw here of about more than 1 meter per second, about 1.5 meters per second within an hour, basically, is replicated both in HARPS North and in HARPS South, which is excellent news that clearly this is the sun actually changing with 1 to 1.5 meters per second at that time. And it's not actually your instrument suddenly going wonky or your atmosphere suddenly going wonky, because it's literally 2 different atmospheres that it went to. Well, it's the same atmosphere, different location on Earth. Now, what you at the same time can see that over here is that we don't always agree as well as we would want. So clearly there's still some work to be done. But overall, it was nice confirmation that several of these variations are indeed the sun just being the sun. In the bottom, you can see the difference for where HARPS-N and HARPS overlapped, and the RMS of that is about 0.43 meters per second, which is our average error for solar observations within a day. Anyway, so this is beautiful, and as you can see here at the end, that is not really white noise. Clearly, there is some sort of systematic in here as well. Now, the other thing that it showed is that if you, because it very nicely followed within a day, follows each other, but if you look at a longer time scale, such as you do here, and I forgot which is which, but blue is the one and orange is the other one, and as you can see, the jumps go, there's multiple jumps happening, and in the residual plot on the bottom, you can see that sometimes they go up to like 2 meters per second difference going from day to day. Now, obviously, that was a sign that, well, something is not going well. This is not supposed to do that. If you agree within a day, you should agree on longer timescales, and if you don't, that is probably something to do with your instrument, or rather with your calibration. So turned out that the way we calibrated could be improved a lot. For all the nitty-gritty details of how this was improved, Xavier wrote a paper in 2021 about this. The good thing of this being a calibration issue is that you can simply, between quotes, go back and re-reduce your entire archive. I put this simply between quotes because Xavier makes his computers work for weeks and weeks on end in order to get the archives re-reduced with a new pipeline, and we're all very grateful, of course. But this has now been resolved, and they do match up much better, but it just goes to show that because you have this amazing data set that overlaps, you can actually track what your pipeline is doing, what your instrument is doing, and you learn, in a way, up until this point, we've learned more about our pipeline and our instrument than that you, in a way, have learned about the sun itself. But that is obviously extremely beneficial for your stellar research, because if you improve the pipeline, you automatically improve your stellar data. Now, why stop at 2 solar telescopes when you can have more? So in the meantime, NUIT also has a solar telescope. Express has a solar telescope. There's plenty of others coming. There's also plenty that will be in the infrared. So this is really only optical solar telescopes that I'm talking about. And we started discussing, given that we now have so many, they all overlap in a way, we should do something with this. So with the people that you see here on the screen, Lily, Eric, Xavier, Joe, and myself, we have been talking for the last couple months, wanting to release a month of data where from all our solar telescopes, where they all overlap, in order for us and the community to understand what is happening, how can you actually combine data sets from different instruments, because we all have slightly different wavelength ranges, slightly different throughputs, and as we know, things like stellar variability are obviously wavelength dependent. So we're hoping that we can learn a lot we already have from combining all the solar telescopes. Now, Lily told me that I could spoil a couple of the pictures. So here you see 3 randomly picked, well, they were randomly picked in the sense that those are the ones that Lily sent me. But they were, in a way, randomly picked because those are also the days where we had a lot of overlap between the instruments. So the colors are the different instruments, and they're written on the plots. On the left, you can see what the sun actually looked like that day. In the sort of shaded color that you see, that's just the original data. And in the actual color, the bright color that you see, that is a 5-minute bin of that data stable throughout that entire day. And you see the same thing as you saw before, in a way, between just HARPS and HARPS-N, is that several of those variations that we see are tracked really well between all the instruments. But at the same time, we don't always agree as well as we would want, which shows that in one way, yay, our instruments work really well. In another way, well, clearly there are still some systematics about our instruments and our data and our pipeline that we're hoping to understand. So within a day, again, we have rather good agreement. A lot of our issues are indeed, again, with doing that on longer timescales. But here is if you just look within a day, if you take all of them and you apply an offset per day so that they all match, and then you take the overlap between two particular instruments and you look at the residuals if you subtract one from the other. So it's very similar to what I showed before of just HARPS and HARPS-N. Now, if you look here, you see all 6 combinations and the total overlap within that month that they gave. And now, obviously, it makes sense that HARPS-N and NUIT only overlapped for 35 minutes in that month. But that is because they are the furthest apart. Then you express and NUIT being on very similar places, they actually overlap for almost 59 hours. What you can see is that we stay well below 0.8 meters per second and often below 0.5 meters per second of the RMS that is left in our residual. So again, that is confirmations that our instruments are indeed stable. That is kind of within a day, that is. But we can't forget the fact that we obviously still have more work to do, but this is proving to be one very useful experiment that we're doing. We are working on getting the first paper together and involving the community in actually playing with that data and doing more stuff with that, so stay tuned. Now, so far, we really haven't learned much about the sun yet, so it's mainly about the instrument and the pipelines, and in a way that's very, very important, as I said. I'm going to focus a little bit on what we learned from a solar and stellar perspective. First of all, as we probably all know, the scatter that we see in the solar data is very quasi-periodic with the solar rotation. So what you see here is 6 stacked periodograms, each from about 6 different months of solar data. So a stacked periodogram, I'm hoping you all know what a periodogram is. A stacked periodogram basically is that you take a bit of data, you make a periodogram, you add a data point, you do it again, add a data point, you do it again, you add a data point, you do it again. And what you see here is time on the y-axis, period on the x-axis, and the color is the peaks in your periodogram. So the darker it is, the higher your peak, the more significant that periodicity. Now, if you were to do this for a planet signal and stellar data, what you would see is that that color keeps increasing. And what you see for something that is variable and is not static is exactly what you see here, that the color gets darker and weaker over time. Now, if we look at these 6 different semesters that I chose, is what you can see is obviously this the darker regions on the right, that is all related with solar rotation. Now, the solar rotation during those 3 years of data has not actually changed. The solar rotation is stable, but the effect in our data is variable. So the solar rotation, or the value that is being found in the data, actually goes all over the place from like 25 to 32 days, depending when you're looking. So bear that in mind, please, when you put teeny tiny error bars on rotation periods that you extract from radial velocity data. It might not actually be the rotation period of your star. What you also see is that during the highest activity period of the data that we have, again, this is not solar maximum, is that the harmonic rotation period divided by 2 also becomes important. Now, the third harmonic, or second harmonic, on 9 days, we can actually also see in the data, but it's cut off from this plot. Now, other things that we have learned is the way you extract radial velocity. For example, the vast majority of us is going to fit a Gaussian to our common profile. We all know, though, that the common profiles and spectral lines are not symmetric. They're asymmetric because of that convective blue shift, for one. So this is work that has also been done by Simola et al. In 2019, and that I've now quickly replicated with our solar data. And it's basically, rather than fitting it with a Gaussian, which is the gray lines that you see everywhere, so radial velocity on the top, and then 2 periodograms in different regions of period space. And then you fit it with a skew normal and either take the mean of that skew normal of the median of that skew normal to be your radial velocity. And those are the green and the red points. And as you can see clearly from both the radial velocity plot as well as the periodograms, is that by not doing a Gaussian, you can enhance the activity signal, which is in a way opposite that we really would want, and on the other hand, useful, because the way we fit should not enhance the signal of a planet, obviously. By the way you fit, your planet didn't suddenly become heavier. So the fact that you can enhance activity signal by the way you fit it can be useful, even though it's the opposite of what we would want to happen in the radial velocities. But it gives you some assurances that the periodicities that you see are probably not coming from a planet in the first place. Now, other work by, this is all work that has been done on the HARPS-N solar data, by the way. Molly, Kosiarek, and Ian Crossfield have released in 2020 a paper where they looked at our HARPS-N radial velocities, the first 3 years of which are public. The width of the CCF, the bisector, and also some photometry. And what you see here is the different periodograms in over those 4 years. And as you can see that they somewhat look similar in a way, but not always. So again, it's that same thing. A periodogram is not always a good way to get an actual rotation period or other timescales from it, and it can be troubling. ACF has the same issues, actually. There's also a wonderful paper on stellar data, not solar, from Shani Nava in 2020 on the same topic. Now, in the same paper from Molly, she also looks at what GPs can do. So a lot of us are using GPs when modeling the stellar variability in our radial velocities. So she did that both on the source data, the radial velocities, the full half max, and the bisector inverse slope, and she let a GP loose on every year of the data sets, and the results of which you can see here in these violin plots. So it's the 4 parameters of a quasi-periodic Gaussian process: the amplitude, evolution timescale, recurrence timescale, and that other timescale that everybody always finds very confusing, which basically has to do with how much variations you allow within a rotation period. And the different colors, as you can see on the top, are just the different data sets that were used. So what you can see here is that overall they do agree relatively well. The ones that are just in outline is where no priors were used at all, and there you see that the agreement is slightly worse. The prior that eventually was set to make these agree is that the evolutionary timescale should be larger than the recurrence timescale, which from a lot of stellar studies is not too weird of an assumption to make for solar type stars. So whilst they do agree, they don't always agree as much as you would hope in order to use GPs from other stellar variability indicators, let alone if you would use them non-simultaneously. So you also worked from Belinda Nicholson recently on simulated data on the same topic, but not using the sun. Now, a bit of unpublished work that we've done with the solar data. So I haven't found the time yet to publish this, but I will, I promise. So this is basically the periodogram of the radial velocity and all the things that we normally use as these activity indicators for the 6 years of data that we have. And as you can see, they all look suspiciously similar, so similar that you would naively hope that they actually correlate quite well. Well, they don't. They correlate in a way, but there's a lot of scatter, and the correlation is actually rather weak in most cases. So what you can see here is just every indicator versus the radial velocity, with the black dots being all the data and the blue dots being binned over a day, which makes it slightly better, but not that much better. So whilst you do clearly see that there are correlations, and they're not as strong as you would think from the same behavior that you have. And that is because there's a time lag between radial velocity and the indicators. So what you can see here is what we published in the 2019 paper, and it's a time lag. It's a discrete correlation function between radial velocity and fluid half max and radial velocity and the bisector inverse slope. And you see that they're shifted by about 2 to 3 days. And so they do have the same variability, but just 2 or 3 days earlier or later, depending how you look at this. Now, obviously, the fact that they lag will weaken correlation if you were just to plot and try to get a linear correlation. I know that most of you no longer use actual linear correlations in your models, but this should convince you to never do it at all. And also that if you don't actually see a strong correlation between your radial velocity and your indicator, that is not actually a sign that there's no variability in your radial velocities from the start. Now this time lag was already seen in stars. On the top, you have radial velocity, which is, have you ever seen such a nice signing looking curve that was attributed to a planet, but is not a planet? You see 3 indicators, and if I can point you to both the RHK as well as the fluid half max, then you can see it has the exact same behavior, and the peaks are slightly shifted with where the radial velocity peaks are. So we saw this already in 2014, and I'm pretty sure it was seen earlier than that as well by Isabel West and others. So it's not a new thing that we've discovered, but it's there nonetheless. Now, complicated plot, but I want to show you everything in a way. So I've tried to replicate this. So I took chunks of 60 days, and then I moved my window a little so that I continuous chunks of 60 days of the solar data going 6 years in total in time. So time goes from top left to right bottom, and you see in all of them the discrete correlation function coefficient versus the time delay. The x-axis is all on the same scale, -10 to 10. The cross is there to guide your eye for 0 and 0. The y-axis are all on the same scale from -1, fully anti-correlated, to +1, fully correlated. And as you can see, in most cases, you do nicely see that this is, I can't remember for which indicator this is, but they all qualitatively look the same. As you can see, everything is shifted almost consistently. Sometimes the pattern actually slightly looks different, like on the top row here. That is when there's actually multiple active regions then, and that is also when, for example, the first harmonic becomes so important in our data. There's other, when we go to solar minimum, what you can see here is that the data is not correlated with activity indicators at all, not with a shift, not normally, this is actually around 0. I didn't put a horizontal line there. This is what the data spit out. There's no correlation there. And trust me, the variation is not 40 centimeters per second. Now, another complicated plot, but to see this, what happens over time. So I extracted the correlation coefficient if you would not account for a shift, and the correlation coefficient if you would allow for a 2-day shift, which is on average what all of them are shifted with. So the blue is the correlation coefficient without a shift over time from all these chunks that you can see. And the green is if you account for a 2-day shift. Now, the green is usually on top of the blue, which we knew that already, obviously, and that our correlations get stronger if you account for that shift. In some regions, and I want to point out around 8,000 here, it actually goes from close to 0 to 0.6, 0.7. So again, if you were just to use a linear correlation coefficient, that is not necessarily a sign that your data isn't having measurable stellar variability. Now the middle and the bottom plot is for the same data set, but where I bin the data per day in the middle, or where I take a random point per day. Taking a random point per day, only the one, is usually what we tend to do for stars, and you do see how you weaken out a lot, and how a lot of the things that you could measure before now significantly get weaker a little. So if you are in the luxurious position that you can observe multiple times per night for your star, that might be recommended. I want to thank James Hazard, my summer student from last year, who started looking into this. Now, the final thing I want to talk to you about in my final minutes is that because we have this data set where there's effectively no planets, and we know that for sure, it is the perfect data set to test new tools. I will already put a caveat here. It is not the perfect data set if your new tool is reliant on the different motions of tellurics and stellar lines, because for the solar data, they don't actually shift. So for stellar data, for example, because of our own motion going from -30 to 30 kilometers per second, tellurics and stellar lines do shift with one another. For our solar data set, obviously they don't. So if your method is reliant on that, the solar data set might not be the perfect data set for you. Now, I want to quickly point out a couple of things. I'm not going to go into details. I'm just going to point out what it has been tested on. So we have scalpels from Andrew with the paper there. We have tested neural network with Zoe with the paper there. There's Fiesta from Zhao et al., not Lily, I think, that has been tested on the solar data. And there's plenty of others that I probably forgot. But I want to quickly find the time to highlight my brilliant PhD student, Florian Linhart, who has been working on enhancing the LSD techniques, and that stands for least squares deconvolution, not the other thing, and has both designed an MMLSD pipeline and the ZLSD pipeline. The MMLSD pipeline, which stands for multi-mask LSD, has been published recently. The code is online, it's on his GitHub page, and we have confirmation that you can make it run on Windows as well if you would want to. And other people on Linux and Mac have also successfully been able to use it. We're currently working on ZLSD. The paper was submitted last week. If you are a referee or become a referee, please be nice. So basically using LSD plainly is not at all different from cross-correlation. You basically have a spectrum, you have a mask, you slide one over the other, and you end up with an average profile of your spectral lines, which you can then fit with whatever you want to extract the radial velocity. We are still fitting with a Gaussian. So in that respect, it's not different than a cross-correlation function. We're using LSD because it is a slightly more flexible way of doing things. So it allows us to extend. Now, doing the plain MMLSD, the thing that makes it different is that we're using a grid of different parameters that can be tuned, and we're using in effect multiple masks at the same time to get our radial velocity time series. That is not consciously trying to account for stellar variability, but we do in a way already. So you see the periodogram here of Kepler-21. Which is a rather active solar type star with a known transiting planet. And on the top, you see it from CCF radial velocities, and on the bottom from the MMLSD radial velocities. The purple line over here, that is where the transiting planet is. And as you can see, we enhance that peak with the MMLSD radial velocities. That whole mess over here on the right, between 10 and 20, that is what was attributed to stellar variability. And as you can see, it is reduced in the MMLSD radial velocities, even though we did not consciously try to do that. So that is a yay already in a way. Now, the extension that has just been submitted is that we want to include Zeeman splitting in the process in order to extract that unsigned magnetic flux that the paper from Raffi showed is such a good tracer. Now, magnetic flux has traditionally either been extracted from polarized spectra or from stacking intensity spectra. What we want to do is to do it on individual non-polarized spectra in order for this to actually be a useful simultaneous activity tracer for our radial velocities. So in the picture here, you see how Zeeman splitting works. Essentially, it comes down to the fact that if there is a magnetic field your spectral line will be split into 3 components. Because that split is really not that large, what you end up seeing is the pinkish purple line. So you basically see a slightly broadened line. Now, every spectral line is differently sensitive to the magnetic flux. If you combine all that knowledge of how a spectral line should differ, and you apply it to residual spectra, because you can't do it on the actual intensity spectra, you do have to subtract a master spectrum that you can create by adding all your spectra on top of one another. We've seen the features before in, for example, Thompson et al. And also Wise et al. I think that some lines are differently responding, but if we use that knowledge on all the lines at the same time, we can, in effect, get the unsigned magnetic flux from the individual non-polarized intensity spectra. What you see here is the SDO value in purple, RHK, which is also an excellent tracer, in green, and orange, the new indicator that Florian now extracts. And as you can see, they trace each other out rather beautifully. You could say, hey, can't you just use RHK, because we had that already. Some issues with that is that for stars that do not have a lot of flux in the blue, or spectrographs that do not actually observe in the blue, such as Carmenes, you can't get an RHK always, whilst this method works wherever your wavelength range is. We've also tested it by looking at the different correlations with radial velocities, including time lags and everything. And it is for the sun and for presumably for solar type stars, the strongest, most correlated indicator that we know. So it's in review. We hope to release it soon. The code will become public so that you can all play with it and have a lot of fun in finding the teeny tiny planets. I'll keep the lessons that we've learned so far on here, but don't forget, having a sun as a star is both useful for your instrument, your pipeline, as well as learning for the stars. Thank you.
Awesome. Thank you so much, Annelies, for a fantastic talk. Yes, much clapping in the audience. Let's open it up for some questions. So feel free to raise your hand on Zoom and I'll call on you. I see Andre up first, so go right ahead.
Hello, thank you for the presentation, Annelies. I have a small question on the comparison between the different instruments. The radial velocities that you computed, were they computed using the same wavelength range that is common to all instruments? Or just use whatever comes from each instrument and look at it at the end?
That is an excellent question. So we talked about this long and hard. Currently, it's just the standard ones, but we are experimenting with using the exact same wavelength ranges. But you still have issues with that because our throughputs are not actually the same at all these wavelength ranges. The orders overlap very nicely, so the actual orders of all our shell orders, but that's mainly because of the people making I forgot the name now. I'll make the same one, so the orders are bound to be in the same place for all our spectrographs in the end. It's a simple hardware issue. But yeah, we are looking to how can you actually extract radial velocity from the different instruments that are genuinely comparable from the same wavelength, as much flux everywhere. It is an extremely hard thing to take into account. You are muted, Jen.
Thank you. Other questions from the audience? Eric Ford, go right ahead.
So the thing that most stuck out to me was when you show those solar telescope comparisons, we see there really are these 1 meter per second over 1 hour features. And a lot of work has sort of focused on the long rotationally linked variability, where there's a good chance we could, map out a 2-day lag and try to move things. So I guess I'm curious to hear what are your thoughts on the best chances we have to be able to deal with those 1 meter per second variations on sort of hour timescales for a star where we don't have the luxury of observing it all night or all day?
Yeah, so that's an excellent question, and in a way, I find that picture rather concerning. It is very scary that the sun can do that on timescales that we typically don't get data for, and thus are not able to track. So to be perfectly honest, I don't know. The only, it has nicely shown, and especially the other one where I took the full data set, compared with a random data point, and how much you blur things out in a way and making it a bit worse. The only thing that I can think of on the top of my head is that from time to time you do sacrifice and spend an entire night on your object occasionally. If that in a way that it might or might not be extrapolatable, yes or no. Then again, the other thing that you can do is that you can rely on the fact that perhaps we do have to test this still in detail, but if that magnetic flux measurement that we get out, if that is such a better tracer and it would trace these short things, then that is just an activity mapper that you can use and be comfortable that it did that. So finding a much better activity indicator, or a combination of better activity indicators, may be your best bet.
Do you know of studies that have looked for correlations, not on month timescales, but just for near those short-term features to see what activity indicators are best correlated or at all correlated with those short-term variabilities?
Very short time, not that I know. I know that we should have the luxury to be able to do that, but not that I'm aware of that we have looked at in detail. I know that others like Mortier are very interested in that as well. Florian and I did look recently at 2 days of SDO data, where rather than taking 4 pictures per day, we asked for all of them and almost broke my hard drive. I got the magnetic flux from that, and the magnetic flux, unfortunately in a way, goes rather smooth, but it varies with about 6, 7, 8 hour timescales that were couldn't really understand yet, but it doesn't scatter.
Did those overlap with one of these features that did have an hour sort of timescale?
No, we were not that smart.
Okay, thanks.
Okay, other questions from the group? Johanna, go right ahead.
Thanks for a great talk, Annelies. I'm excited to read this new paper. You probably said this and I just missed it. What is the integration time for these solar telescopes typically? Like for each point, how much time is there?
That is a good question. I'm pretty sure it's different for all 4 of us. So HARPS-N does a 5-minute exposure time, and it's about 5 minutes and 12 seconds integration time. That one I know for sure. Eric says it is 55 seconds.
Okay.
But they're slightly different everywhere. I know that the express solar data goes with signal to noise rather than exposure time, so they have a variable exposure time. We have the HARPS's at least have an extremely fast readout. So yeah, we only after 12 seconds we were integrating again.
Okay, this is on my mind because I've been reading up recently. So this is a tangent, but one of the stars that I'm observing, like exoplanet atmospheres, has flares. It's an M-dwarf, but these flares can happen on like microsecond timescales. And so I'm just wondering, I don't know if that's happening in solar type stars, but if we're trying to look at very, very short-term effects, if the RV observation integration is quite long, I'm just wondering if it would capture that. So anyway, that was just me thinking loud.
Yeah, so flares in itself, well, as far as I know, they're not too big of a problem in radial velocities for solar type stars, for the simple reason that they just simply don't flare that much. I'm hopeful that by the time we do reach maximum again, and the fact that we'll by then predictably will have at least 6 optical solar telescopes, we should learn a lot. Because that is the only downside of all our solar telescopes, that we haven't yet covered a solar maximum, and the star, the sun is not particularly the highest amongst its friends in the obviously for M-dwarfs, etc., that's what I said. That's where the caveat comes from. Stars that flare more, how are you going to test that?
A whole different ballgame. Yep. All right, thank you.
Okay, we got time for one more question. If there's anything burning in your minds among the audience.
Don't burn your minds.
I have one actually. So the work you were describing that Florian's doing at the end of your talk, are there any specific requirements for the data for it to be amenable to that kind of analysis? Are there certain parts of the spectrum you want to be covering, signal to noise requirements you want to hit, et cetera? Or is this, we can apply it to any retroactive data?
For signal to noise, I have good news. We can do it on signal to noise down to, we've tested down to 60 signal to noise. Obviously, our data is rather good for the sun, obviously. At some point it won't work anymore, but given that most of us are looking at bright stars, we do work at signal to noise of about 60, so that is the good news. You obviously want to cover enough of a wavelength range because you need a fair amount of lines, because there's a whole bunch of spectral lines that are not actually contributing here. There's a whole bunch of spectral lines that are really not that sensitive to changes in the magnetic flux and will thus not be helpful. So you need to make sure that you cover enough. Going to the infrared in a way should be better because the Zeeman splitting gets worse with wavelength. So in a way, it should get better in the infrared. On the other hand, as we all know, tellurics are a mess in the infrared. So the effect might cancel each other out. We haven't tested that yet. We haven't gotten access to infrared data to try that on. The other thing I would say is resolution. Obviously, you want to have spectra from a high enough resolving power. So the HARPS are about 115,000. That's the one thing that we haven't tested. How low in resolution can you go for this to still work? Because you do need to be able to distinguish that feature. And if your resolving power doesn't actually allow for that, then you won't see anything.
Very cool. What do you think about R of like 65,000, which is what I think PRV is operating at in the H and K band? So we can get you near infrared, but the resolution is notably lower.
No, yeah, but it's a good test. All of these things can be good tests in a way. Espresso having 150,000, whilst if you just visually look at the spectra, they look very much the same as the one from 115,000, with the differences that you can actually resolve much more of each spectral line, which in the end is the thing that's gonna matter. It's like you see the same spectrum with 115 and 150,000 for most stars, but you resolve within the spectral line, and in the end, that is where the changes happen. So.
Gotcha. Okay. One more. Bryson in the chat says PRV needs a solar feed. Agreed. One more question from Shweta. Go right ahead.
Hi, I'm going to try. So, Annelies, is there a limit on the V sin I? If the rotation of the star is higher or lower, you won't be able to, because it's still broadened the line, so you're detecting the broadening.
That is a very good question. We have not tested that, and that is a very good question, though. So we've only tested it on the sun for the simple reason that we know the magnetic flux, and this was a trial one, of course. And we have not sped up the sun in order, if you know what I mean, we have not added additional V sin I to our spectra, but that's an excellent idea. I see no reason why you can't convolve the solar spectra to make them broadened more with V sin I, and then test it again.
Thank you.
We have not sped up the sun, I think, is my favorite assertion that has been made in one of these colloquia.
And that's recorded, so no.
Okay, with that, we are just over the top of the hour, so let's wrap things up. Thank you again so much, Annelies, for agreeing to speak and for giving a fantastic talk. The recording will be posted to the Google Drive, hopefully later today, if not tomorrow, so folks can catch any bits of it you want to revisit. And we'll see you next month.